A good day and welcome back. Wish that you had watched our previous video lectures on common emitter and common base configuration. Today we will discuss the input and output characteristics of common collector configuration. The learning objectives would be to obtain the input characteristic graph of a common collector configuration and also the output characteristic graph of the same configuration. So this is how the terminals are arranged in a common collector configuration. The collector terminal forms the common terminal between the base and the emitter. The base collector terminals would form the input side and the emitter collector terminals would form the output side. As we had discussed the current gain of common emitter and common base configurations in the previous video lectures, here we will get the current gain of a common collector configuration. In order to understand what gain is and what current gain is, please refer our previous video lectures. Current gain is given by output current by input current. The output current of a common collector configuration is your emitter current, and the input current of the configuration is your base current. So the current gain, the DC current gain of a common collector configuration is given by alpha, which is equal to IE by IB. Now we will understand how do we obtain the input characteristics of the common collector configuration. This is the experimental setup. In order to understand the procedure, how the input characteristics are got, please refer our video lectures on common emitter and common base configurations. So here you have the common collector terminal. The input voltage is the voltage across your common base terminals. The input current is your base current. The output current is your emitter current. And the output voltage is voltage across collector and emitter terminals. Normally, this representation is given as PBC. The suffix, the second alphabet of the suffix is always the terminal that is going to be the common terminal, right? So we would write this as BBC and we would write this as VEC. The second alphabet of the suffix would always denote the common terminal, right? We will have this in mind. So VBC is the input voltage, VEC is your output voltage. By going with the procedure, the same procedure of the common emitter and common base configurations, the input voltage being VBC, the input current being IB and the output voltage being VEC. Now what we are trying to do is we are trying to obtain the input characteristics by changing the input voltage and noting down the corresponding input current, having the output voltage to be constant. So this is what we will do, and the procedure is one and the same as that of your common base and common emitter configurations. We will try to get the input characteristics of common collector configuration using the equations. This equation we have already seen in our previous video lectures. Please do refer to understand how we obtain this equation. We take this equation and we try to bring it for common collector configuration. PCB now becomes VBC because this denotes the common terminal. VCE becomes VEC, the common terminal, when VBE is kept as such. So this, on rearrangement, we get this equation. VEC minus VBC would become VBE. And we will try to plot or rather take a tabular column to understand. Before that, we will understand another important concept. When VBE increases, the base current will definitely increase. Having this in mind, we will get a tabular column by taking different values of VBC, VEC and VEC. We will keep VEC to be constant. The output voltage is kept constant for a set of reading. So we will keep it at 1 volt, say for example, right? And we change VBC. Now that is how you obtain the input characteristics, is it not? We change VBC and note down your base current, right? So VBC changes for a constant output voltage. Now VEC is going to be kept as 1 volt. Now we change VBC, I keep it at 0.1, right? So these are all random values that we take. 0.1. So VBE is 0.9. When VBE increases, IB increases. So the current IB is present. Now we will take, when VBC is increased to 0.5, VBE is 0.5, right? When compared to the previous value, it has reduced, and so IB will start decreasing, and when we take VBC to be 1 volt, say you take it over here, VBC to be 1 volt, the voltage across base emitter terminals becomes 0, and so automatically you will have IB to be 0. Before that, now we will go for another tableau column, another set of reading. Now I have changed VEC to 2 volts to get the second set of readings. I want the second graph. Is it not, right? So I will make VEC to be 2 volts and I will repeat this experiment with the same set of values, right? So to understand how IB is. So I will keep it at 0.1 volt, the same 0.1 volt, and I could see the value of VB is 1.9, which means that the base current is greater than the base current of this with the same set of values, right? I'm comparing these two tables and I notice that the base current when VEC is equal to 2 volts is greater than the base current when V is equal to 1 volt. This happens for the remaining set of readings, right? You could notice that no, this is 0.5 and this is 1.5. The base current is still greater. Now it is 0, here it is 1. Still the value of base current is greater, right? So with this set of readings, now we will try to understand how are we going to plot the graph. We will obtain the input characteristics of common collector configuration with few concepts in mind. When VBE increases, your base current increases, and when VBE decreases, your base current will also decrease. From the equation, we have obtained this table. We have kept this emitter collector voltage, the output voltage constant, and we have increased the input voltage, which is the base collector voltage. And from the equation, by substituting the values of emitter collector voltage and base collector voltage, we have obtained the value of the base emitter voltage with these values. You could notice that when base collector voltage increases, your base emitter voltage decreases. So when base emitter voltage decreases, your IB will also decrease. So this is the relationship that we have, and we will plot it in this graph. First, we will take the base collector voltage to be 0.1, keeping emitter collector voltage as constant. We increase the base collector voltage. At 0.1, we notice that the value of the base emitter voltage is 0.9. For this base collector voltage of 0.1, we have the base current to be 20 microamperes, say, for the base emitter voltage to be 0.9. Now we increase the base collector voltage at 0.5. At 0.5, so this to be 0.5, the base emitter voltage has decreased from 0.9 to 0.5, which means that your IB will also decrease, and we assume it to be, say, 10 microamperes. The base collector voltage is still increased to 1, and you notice that the base emitter voltage is 0, and as a result the base current is 0 at the base collector voltage to be 0.1. And when you join all the points, you do get a graph like this, a declining graph sloping downwards for VEC to be when VEC is 1 volt. This is one set of reading. Now we need to take the other set of reading that we have already discussed in the previous slide. So this is the first set of reading that we have got, and these are the two tables for comparison. And you could notice that we have increased the output voltage from 1 volt to 2 volts. And when you compare the base collector voltages of this table and this table, you could notice for this 0.1 volt, you could notice that there is an increase in your base emitter voltage from 0.9 to 1.9. And as a result and as a consequence, you also notice that there is an increase in your base current. Say when the base current is 20 microamperes at VB equal to 0.9, it can be a higher value. Say it could be 30 microamperes when it is at 1.9 volts. And so when you plot it, right, you could see when VBC is 0.1 volt, you could see that 20 microamperes, now it is 30 microamperes. And at 0.5 volt, earlier it was 10 microamperes, now it could be a greater value than this 10 microamperes, say 15 microamperes. And you have a plot here. This is 10, this is 15. And when you go for the next, you see there is still a higher value of base current when you compare it with the previous value. And finally you get a 0 VBC equal to 2 volts. Now when you join all the points, you get another declining curve for VC equal to 2 volts. And when you consolidate, you do have a graph like this. We have understood the input characteristics of a common collector configuration would look like, and we have also reasoned out why the graph is obtained in this fashion. Now we will move on to the output characteristics of common collector configuration. The experimental procedure is the same. If you want to know the procedure, you could refer the previous video lectures of mine. The input and the outputs will alone change. The procedure is one and the same. The input voltage is voltage across the base and collector. So this has to be base collector. Always have in mind that the second alphabet in this voltage notation always refers to the common terminal. Here, as it is common collector, we need to write it as VBC. Similarly, here the output voltage has to be written as VEC, the voltage across your emitter and collector. The input current is your base current and the output current is your emitter current, which is measured in milliamperes. So the output characteristics is going to be obtained by changing the output voltage VEC and noting down the corresponding emitter current, keeping the input base current to be constant. So this is how you will obtain the characteristics, and this characteristics is very similar to that of common emitter configuration, where here you will have it to be VCE instead of VEC, right? In common emitter configuration you will have it as VCE, and the output current would be collector current in common emitter configuration, whereas here it is IE, the emitter current. And we also know this well-known equation, IE is equal to IC plus IB. As IB is very negligible, or rather as it is in terms of microamperes, we could approximate IE is equal to IC is approximately equal to IC. The input current, which is the base current, is going to be the same for both common emitter and common collector configuration. So the graph would exactly resemble the output characteristics of common emitter configuration. We have discussed in detail about how we obtain the output characteristics and why the curves look in this fashion in the video lecture of common emitter configuration. Please do have a look into it to understand the concepts. With this, we come to the end of the configurations, and in specific the common collector configuration, where we have discussed the input and output characteristics. Hope you have understood the concepts. If you like the video, please do click the like button, post your comments, and remember to subscribe without fail. Thank you so much for watching, and meet you again in another interesting video lecture. Thank you so much.